Dear students, welcome to today's lecture, and we have reached section 5.4.4, and we will focus on the second fundamental theorem of asset pricing. But before we do that, we recall a few things from last lecture, and particularly we start with the complete market. So remember, a market is complete if every derivative security can be hedged. So a derivative security is a financial option, for example, and every security can be hedged means that there is a self-financing or a hedging portfolio such that at any time, little t between 0 and capital T, the value of the portfolio process xt is equal to the value of the option vt. So xt is the value of the portfolio at time little t, and vt is the value or the price of a derivative if sold at time t. The fair price, we must say, because the true price is always a little bit higher than the fair price. And this was the setting from a few lectures back. We know the payoff. For example, for a European call, we know that the payoff is the maximum at st minus k and 0 at final time, capital T. And because we know that the discounted option value is equal to the discounted portfolio price, is a martingale under P tilde, under the risk neutral measure, we find for the solution of the option value at any time little t, prior to capital T, that it can be written as the expectation under the risk neutral measure, so E tilde of e to the power minus the integral from little t to capital T Ru du, with R the stochastic interest rate or the constant interest rate, times the payoff at final time of the option V at time t, given the filtration up to time t. And this is, as we know, this discounting term here, that is the discount term at final time divided by the discount term at time little t, again, times the payoff given the filtration up to time little t. And then this term here that is measurable, so that can be taken out and can go to the left-hand side. So we end up with the discounted option value is equal to the expected value under the risk neutral measure of the discounted payoff at final time, given the filtration at time little t. So we recall that the discounted portfolio process, 0 less or equal to little t less or equal to capital T, that satisfies the following. Again, it's a self-financing, so at any time, the value of the portfolio process is equal to the value of the option, particularly for the writer, this is at time t0, so the value of the option at time t0 should be equal to the value of the portfolio at time t0, and that can be seen as the option premium, so that is the money that is received by the writer when he or she sells the option. Secondly, the discounted portfolio process in the time frame of the contract is a martingale under P tilde. And that has been written out a few lectures back. And there we have seen that the discounted portfolio process could be written as x0, as d0 is equal to 1. S0 plus the sum over the number of stocks. And because we are in a multidimensional setting, I runs from 1 to m, the sum over the number of dimensions, the number of Brownian motions. J runs from 1 to d, the integral from 0 to t, delta IU times the discount factor at u times the ith stock value at u times the volatility matrix elements sigma ij at u times dw tilde j u. This we have derived, and here we have delta I. Delta I is the number of stocks of stock I that should be kept in a portfolio in order to to compensate for any risk. And then we had the martingale representation theorem, the multidimensional version that tells us there is an adapted process, gamma 1, gamma 2, up to gamma d in the contract period, such that this discounted portfolio process being equal to the discounted option price is equal to x0 plus the sum j runs from 1 to d, the integral from 0 to t, gamma ju, dw tilde ju. So the martingale representation theorem tells us there exists a vector of gamma j elements, a vector gamma j with gamma 1, gamma 2, etc. There exists a vector so that this is valid. Because this is a martingale, there should exist a gamma j. That was the martingale representation theorem. And then we had the notion, of course, that for this gamma j, we can substitute the factors that we found on the previous page. So gamma ju is equal to the sum, I runs from 1 to m, delta iu, discount at u, s iu, sigma iju, and j runs from 1 to d. So this tells us that we have a solution of the above systems for the variable delta 1 up to delta m, and it allows us to build a hedging portfolio, a so-called self-financing portfolio. In the next lecture, we will see a more practical example where we get a bit more concrete idea about this hedging portfolio and the results. So how hedging looks like in practice, that will be shown in the next lecture. Now we reach theorem 5.4.9, and that is the second fundamental theorem of asset pricing. And it says the following. Suppose we have a market model with a risk neutral measure P tilde. So suppose we are in a market with a risk neutral measure. Then the market is complete, which means that every security, every financial option, every financial product can be hedged if and only if P tilde is unique, if and only if we have a unique risk neutral measure. Well, the proof goes two ways. First, the proof goes from left to right. So it says the market is complete if and only if P tilde is unique. Let's look at that as follows. Let's assume that the market is complete, but let's assume that we have two risk neutral measures, P tilde and P tilde prime. Then we will show that P tilde prime should in fact be equal to P tilde. And under both measures, the discounted price process would be a martingale. Now let's see what it brings. Well, let's look at a specific example. Let A be an event in the filtration F, arbitrary, and let's consider a specific derivative security. Let's consider a specific option, an option which has the following payoff. It's 1 over dt, so 1 over the discount, times the indicator function that A will happen. So we get a payout of 1, essentially. We get a payout of 1 when the event happens, and we get a payout of 0 when the event does not happen. That is what this indicator function tells us. Then we have added the omegas here explicitly just to indicate that, of course, this is a random event. When the event happens, we get paid out, and when the event does not happen, we don't get paid out. So because the market is complete, that is our assumption, right? Assuming that the market is complete. Because the market is complete, there must be a portfolio process X, little t in the contract time, such that at every time point xt is equal to vt. That is the notion of complete markets. And of course, the discounted portfolio process is a martingale both under P tilde and under P tilde prime in this specific case, right? In this specific setting of the proof. Now let's write it out. Let's write out what does it mean that the probability under the p tilde prime measure that A occurs. Of course, by definition, that is the expectation under the p tilde prime measure of the indicator function of A. So the indicator function, which is 1 when A occurs and 0 otherwise. And because we are in a complete market, right? We can write this. We can write this as the discounted option price is equal to this indicator function. And because we have a complete market, we know that this is then also equal to the discounted portfolio value. So we can substitute that. That is what we do in this next step. So this expectation is identical to the expectation under the p tilde prime measure of the discounted portfolio process at final time. Now this is a martingale, and because this is a martingale, it's equal to the discounted portfolio process at time 0. Expectation under the measure p prime tilde x0, and that is equal to x0 because that is known at this point. So that is x0. But at the same time, we know that x0 is then also under the p tilde measure. It is a martingale, right? That is also given. We had 2 of these, so it's also under the p tilde measure. So it is the expected value under the measure p tilde of the discounted portfolio process at final time. That is the expectation under the p tilde measure of the indicator function of A. And that is, of course, the probability under the tilde measure of A. And so we see that the probability under the p tilde prime measure is equal to the probability under the p tilde measure. So therefore, we see that p tilde prime is equal to p tilde under this assumption. And that is one way of the proof. So therefore, p tilde is equal to p tilde prime, and we have a unique risk neutral measure. Now the other way around. So we go the other way around. So we assume that P is unique. P is unique, then the market should be complete. So that means that every security should be hedged, can be hedged. And there you see something like the martingale representation theorem appearing. We assume that the risk neutral measure P tilde is unique. And first of all, note that this implies that the underlying filtration of the Brownian motion must be generated by the Brownian motion. Otherwise, for sets not in the filtration of the Brownian motion, one can assign any probability to those. Now, as a consequence of this uniqueness, the uniqueness of P tilde, we know that the market price equations must be satisfied, right? So that those market price equations, if you recall from a previous lecture, it was alpha IT minus RT, RT the interest rate, is equal to the sum, J runs from 1 to D, sigma IJT, theta JT, I runs from 1 to M. And these theta J's, they are important in this matter, right? As a consequence of the uniqueness, we know that the market price equation should have a unique solution theta t, consisting of the elements theta 1t, theta 2t, up to theta dt. Now, if we look at this from the matrix point of view, this set of equations, I runs from 1 to m, that can be written as a matrix vector equation. And again, these are m components. So on the left-hand side, we have a vector of m components, alpha 1t minus r, alpha 2t minus r, up to alpha mt minus rt. That is the left-hand side. And the right-hand side is, well, this is a matrix vector equation. So for each I, we have a sum over j elements, and we can write that as a matrix vector. So the first one is I is 1 and j is 1. That is over here. And then I stays 1 and j runs. So here is sigma 1d, theta 1 up to theta d. And we can complete this matrix vector formulation with a sigma 2,1, a sigma 2d, up to a sigma m1, sigma md. And in fact, this set of equations here, you can be assured that that is identical to this matrix vector multiplication system. And we were looking for theta 1 up to theta d. And if we call this matrix A, and we call this right-hand side B, and we call this a vector that we are looking for X, then we have in linear algebra formulations, we have a matrix vector equation AX equals B, and we are looking for the X. Now we have a unique solution, right? That is given, right? P tilde is unique. We have a unique solution. X in our A x equals b, it's x, it's theta 1t up to theta dt transpose. Transpose we also write like this here, transpose. And the matrix A is m times d. Yeah, it's an m times d matrix, and it satisfies that the rank of A, if we think again in terms of linear algebra, recall that we talked about the rank and the range and all these things. The rank of A is equal to D in this case because of the unique solution. And that is then also the dimension of the range of A. The dimension of the range of A is the number of linearly independent column vectors, and that is equal to D. Recall that also the rank of A transpose is equal to the rank of A, and that is D in this case. Now we want to show that the market is complete, so we consider a derivative security with a payoff V at final time t, and Vt is Ft measurable, of course. So what we need to show in order to show that the market is complete is that it can be hedged. And this is, as before, equivalent to finding a solution delta 1t up to delta mt for the system that we have just defined. We had a system with gammas equal to this expression, and I divide left and right hand side by the discount term. So we get a system gamma j t divided by the discount at t is equal to the sum I is 1 to m delta it sit sigma ijt, where j is 1, 2, 3 up to d. And also this we can write in a matrix vector formulation, but we will note that this is a little different from the previous formulation. So now it's with d terms, so we have a vector with d terms, so it looks a little different here. So these are d terms here, gamma 1t over the discount term up to gamma dt over the discount term. This is a d vector. And then we have our matrix here. If we look carefully at this system, now we have a sum over m, a sum over m. So we have, if in order to match dimensions, we have m terms here, sigma 1t up to sigma m1t. Those are here. And they are multiplied by m terms here, delta 1t s1t up to delta mt smt. So that is a matrix vector multiplication. And we complete this volatility matrix by completing it here with sigma 1 dt up to sigma m dt. So this is slightly different from before. We go from sigma 1 to sigma m1 here. And in the previous formulation, we went from sigma 1 to sigma 1d. And here we had sigma m1. So if you look at, if you compare this matrix A with the one that we are dealing with now, you recognize that we are dealing currently with A transpose, right? Sigma M1 is on this part of the diagonal, sigma 1D is on this part of the diagonal. Sigma M1 is here and sigma 1D is over here. So in fact, this is a transpose. This is, we are dealing with a D times M matrix in this case. And if we call this vector here Z, then this is a transpose and this is Y. And we're looking, essentially we're looking for Y because we say gamma is given, we are looking for Y. Now, again, recall from linear algebra, first year linear algebra, that the rank of A transpose is the dimension of the range of A transpose, and that is D in this case, because A transpose is a matrix that maps Rm functions to Rd. Right? We have Rm to Rd. And the range of A transpose that was defined as Z in Rd, Z is equal to A transpose Y for Y in Rm. And the range in this case is then indeed Rd. They have the same dimension. And having the same dimension is a good sign, of course. That means that for all Z in Rd, there is a Y in Rm such that Z is A transpose Y. And that is a sign, an important property of completeness. For all Z, there is a Y such that Z is equal to A transpose Y. So particularly if we choose Z gamma 1 over the discount factor up to gamma D over the discount factor transpose, then there exists a Y in Rm such that Z is A transpose Y. This concludes our proof that there is in fact a complete market. So if we set Y sub I equal to delta IT SIT, then we have delta IT is equal to Y sub I divided by S sub IT. So we have a hedging portfolio and therefore the market is complete. And this concludes the first part of today's lecture. I thank you for your attention.